All right, so we're into chapter 17 now. On the topics of, basically we're focused on entropy. What is entropy and how does it affect chemical reactions? But the lab is not going to be parallel with this. I couldn't find a good entropy lab. So we're going back to actually the first exam material, molar mass by freezing point depression. We're going to use a colligative property. And should be old hat by now. Okay, so let's talk about thermodynamics. That's where we're headed. Remember, in kinetics, we had a study of reaction rates. And reaction rates depend on pathway. You know that's true because of the effect of catalysts that have on reaction rates. The catalyst supplies an alternate pathway for a reaction, one which is actually lower activation energy. So in this diagram, where we're talking about where we have the reaction progress and energy, you remember that where you start with reactants and end with products, and then in the middle, this is where kinetics takes place. If it's very high here, there's activation energy, then the kinetics are going to be relatively slow. But if we can put a catalyst in there and drop the activation energy down, then we can speed up the reaction. But the source and the destination are still the same. And that's an area of, we've studied so far, equilibrium. And thermodynamics picks up on equilibrium again. I apologize. I don't know what to do with that thing now. And I don't want to go get IT because they'll be in here for half an hour eating up our time. So if that starts to give you a headache, turn around and watch the back screen. So it sort of sits sideways. So if I write something up here, you can see it. Or close your eyes and wait for the video. Okay, so to say again what I said, kinetics has to do with reaction rates. Thermodynamics is an equilibrium situation. So we're talking about a path function for kinetics and a state function for thermodynamics. Just to illustrate, we know that diamond is a thermodynamically unstable form, allotrope of carbon. That means eventually it will degrade into a more stable form, which would be graphite. That's thermodynamics, tells us what the end product would be. But kinetics tells us that it's going to take millions of years to happen, right? So they approach problems from two different directions and you get two different answers. But a study of thermodynamics will help us understand something of what drives reactions, what causes a reaction to occur. Because sometimes you can't explain it with kinetics or with your typical equilibrium discussions. Okay, so what thermodynamics does, and thermo, of course, refers to heat, dynamics refers to movement. So the reaction goes and we follow the progress of heat transfers. So we're picking up on an earlier discussion, I think it was in first semester, discussion of thermochemistry, where we did calorimetry. That was just scratching the surface of thermodynamics. But thermodynamics will allow us to predict the direction of the normal spontaneous direction of a chemical reaction. And by spontaneous, we mean a reaction that occurs without any intervention. When you put two reactants together, the spontaneous direction is the one that produces products. If it's non-spontaneous, then when you put the two reactants together, nothing happens. They're already where they want to be. They're in a stable situation. And the only way you can force them to go to react with one another is to add energy or add a catalyst, do something. But when you just put them together and they react, that's a spontaneous process. So let's consider this thought problem. You have 2.4 moles of gas contained in a bulb at constant temperature of 32 degrees. We have 2.4 moles of some gas in a bulb, and I think we said it was 32 degrees. And the bulb is 4 liters, so volume equals 4 liters. Okay, let's be consistent. Temperature is 32 degrees. This bulb is connected by a valve to another bulb. Okay, so we need to make a connection here with a valve to another bulb. Well, this bulb is 20 liters. Okay, and it's a vacuum. All right. And we assume that the temperature is constant throughout this whole process. Right, we can do that because we made it up in the first place. So what should happen if we open the valve? Is this just going to sit there and let the vacuum go on its merry way? No, we know intuitively what's going to happen is that gas is going to go and it's going to expand and fill the whole space. Okay. So the question is why? Why did it do that? Right? There was actually no chemical reaction involved. It was a physical process. What drives that gas to move into this space and fill the whole space? Did we change the number of moles of gas? No, it's the same number of moles. We've already specified the temperature is going to be the same. The volume did change. Right? Now we've looked at gas laws in the past, right? If we see the volume increase, then what should happen to the pressure? Pressure should go down. That's according to Boyle. But that's just a law. It doesn't explain why things happen. So, let's see. We've got some terms. Let me look ahead just a second. Okay, so we're still going to deal with this problem, so I better leave that up there. What we need is some terms. Right? We know that enthalpy is represented by that value. Correct? We covered that before, didn't we? Okay. So this is enthalpy. Enthalpy is okay, equal to something else, but I got to define my terms first. So this we represent as total energy. We haven't talked about that yet, have we? Internal energy, right? This is internal energy of the system. Remember when I think we talked about thermochemistry, we defined what a system was, right? So this is our system and everything else is surroundings. Or we can isolate all of this, right? Which is what we do in thermochemistry with our styrofoam cups. We have an isolated system. In fact, we isolate this part from the surroundings so that everything that happens in Vegas stays in Vegas. But if we let energy transfer, not matter, energy, this is a closed system. So nothing crosses these boundaries except maybe energy, heat, our little Q. So that's heat flow. And remember, everything is reference to the system. So if heat flows in, then Q is what? Positive, right? We did cover that, I'm sure. And if heat flows out, then the value is negative. Okay. So this is internal energy is the entire assessment, whatever energy is in the system in any and all forms, right? It could be kinetic energy, like the gas molecules are bouncing around. They've got velocity and mass, so they've got kinetic energy. Remember? Mass and velocity gives them kinetic energy, but there's some potential energy here also. And the potential energy could take the form of a number of different things. It could be heat, which is related to kinetic energy, of course. It could be energy of their bonds. They could be molecules like this, and there's a bond between them, or it could be something more complicated, like, I don't know, ethanol. It's got bonds in there, and there are energies associated with those bonds. So all the energy in here, and it could be also with the pressure that's being exerted inside this vessel by a gas, right? So it could be reduced to a discussion of pressure. But everything, all the energy contained in that system is expressed in this term. Okay. This is internal energy. Internal energy. And this is enthalpy. That's the heat potential of the system. Now we've got some equivalents here. I might as well put it up here. Enthalpy is related to internal energy in that it is internal energy plus any changes that occur in pressure and volume. Okay, that seems odd, doesn't it? I just told you that this is all the energy that's in the system, and now we're saying enthalpy is all the energy in the system plus changes in pressure and volume. Well, changes in pressure and volume are effects that the surroundings have on the system. Right. So enthalpy is a response to any effect that the surroundings has on the system. So in that respect, it is a new term. The one I left off was W. That's equal to work. Okay, so if now we're letting the surroundings and the system interact with one another. And work, remember in physical terms, see, I've asked you this question before, right? It's anybody had physics before? Okay, so work in physics is defined as a force applied through a distance. Okay, if either one of these does not change or is not there, if that term's not there, then no work is done. So I can apply a force, but if there's no movement, there's no work. Right? So I can stand here and push on this wall, and I'm applying a force, but it's not moving. So I didn't do any work. But I did apply a force, and that requires energy. Right? So where did that energy go if I apply force? Well, it went into heat. That's the only place it can go. So my hand heats up and the board heats up a little bit. But no work was done. Well, we're going to use that concept for assessing the work that's either done on the system or by the system on its surroundings. And we use this little w, and the same sign convention is used here. If the system does work on the surroundings, work is negative. If the surroundings will do work on the system, the value is positive. Okay. So I think we got all our new terms up there on the board and on the slide. Okay, now let's go back to this problem. we intuitively know that the gas is going to flow through the valve into the vacuum, and it will all be equalized, be the same pressure throughout. But what can we say about these new terms? About the heat term, about the work term, internal energy, and enthalpy. Let's see, am I going to have to do this one cold turkey, or do we have? Well, they're all equal to 0. Right, so I need to explain that. Okay. Was there any? Let's start with enthalpy. No, let's start with internal energy. Was there any change in internal energy? The temperature stayed the same. The gas moved from here to here. But if internal energy is an expression of all the forms of energy that are contained, we didn't do anything with chemical bonds of the gas. The pressure changed, but the volume increased. We did not change anything with reference to the total internal energy of the system. All we did was just rearrange the molecules. Right? So internal energy didn't change. How about enthalpy? Well, enthalpy only changes, since energy didn't change, enthalpy only changes when we see a difference in pressure times volume. Well, pressure times volume, according to Boyle, is the same. Right? The pressure over here and the pressure with the whole system decreased, but the volume increased. So when you multiply them together, there's no change there either. Right? So enthalpy didn't change. How about Q, total heat of the system? Well, we're not letting heat cross into or out of the system, so there's no change in heat. Okay, and we're saying the temperature is constant. So that's another indicator that there's no change in heat, because heat responds to a difference in temperature. So since the temperature didn't change, there's no transfer of heat. How about work? Was there any work done? Well, we didn't move through any distance. Right? We didn't work on the surroundings, and the surroundings didn't work on the system. So there's no work done either. All of them are 0. The reason this slide exists is we're trying to set up the situation where a change has occurred, but we can't explain it with any of these terms. Can't explain that either. I could take care of it maybe with a hammer. So the constant temperature process means that change in energy and change in enthalpy are 0. There's no pressure against which we're working, because this is a vacuum. Right? So when the gas moves, we're not working against a pressure. This is another way of explaining, hopefully better than I did. So there was no work done. And oh, I did leave this one off. This internal energy is also equal to Q plus W. So any heat transferred or any work done assesses the change in internal energy. So since there was no work done and internal energy is 0, then Q has to be 0 too. So all these terms are 0 under these circumstances. What's the driving force for the process? Well, we have to create a new one. We have a new term to try to get at what's happening in this system. And this was introduced in the mid-19th century by a man by the name of Rudolf Clausius. I'm not sure, I don't see German. Rudolf says German, but I'm not sure about Clausius. I think he was, introduced the concept of entropy. Now, entropy was introduced in a mathematical form. And it you have to get at its roots, you have to approach it from a mathematical and statistical direction. But that doesn't mean we still can't use the idea once it's been developed. Then we can get at these problems without actually doing all the math, which is good. He's a fairly stern looking fellow, isn't he? Of course, in the mid-19th century, all pictures looked like that. Right? Everybody had dour looks on their faces. I rarely see any of these old photographs where the subjects are smiling. Okay. So let me see. Let's make room for some more material. I thought this was going to erase better. It is. And the longer it stays up on the board, the harder it is to get off. Okay. So here we have an expansion of an ideal gas into an evacuated bulb. And what you'll notice is we've represented the gas molecules as these little red dots. And what you'll notice too is that when we open the valve, we know the gas spreads out, but when we look at it from a microscopic perspective, we see that the gas molecules are spread further apart. That's the difference between the images. They occupy a larger space. And that represents an increase in entropy. We look at, there are several ways to approach entropy. One is, there is more disorder in the second one than there is in the first one. Order means that they're closer together and they're occupying a smaller volume. And then when they spread out into more space, that's an increase in disorder. And that's one way of looking at it. A change in entropy, if it's greater than zero, we have an increase in disorder. And if the change in entropy is less than zero, we have a decrease in disorder. The natural movement of any system is to an increase in disorder. Now, when your authors, when the writers of the book refer to a spontaneous process as an increase in disorder, they're referring to the universe. But just like when we discussed calorimetry, we can isolate our part of the universe and discuss that part rather than the whole universe. So if we think about the entire universe, everything we know, then we can say that the change in entropy for the entire universe is always greater than zero. In other words, the universe is running down. It's becoming more and more and more disordered. Now, there are local pockets of increasing order, right? That happens. Right? If it didn't happen, then we wouldn't have a sun, right? It'd just be a big ball of nebulous gas. But as it turns out, gravity takes over, pulls all the molecules together. And in the center of the nebula, when it starts to spin, things start to organize under gravity, then you get this ball of hydrogen and helium in the center that eventually, once the pressure builds and the temperature builds, you start getting nuclear reactions and it throws off energy. And it blows a lot of the dust away from the inner solar system until the planets start to form. You get bigger chunks of dust and rocks, and they gather together, and you get planets and asteroids and comets, and things like that. So we do get an increase in order on a local level, but for the whole universe, disorder is always increasing. And for another reason also is that supposedly we have all this mass and energy in the universe, and it's fixed. It doesn't change, but we know that the universe is expanding, right? Edwin Hubble proved that 100 years ago, that the universe is expanding. So if the universe is expanding and you still got this fixed amount of mass and energy, it's expanding into that new space. So that also drives the entropy. We got more space with the same amount of mass, it occupies more space, entropy increases. Okay, so just to drive this point home, a discussion of entropy in terms of disorder is a grossly oversimplified explanation, but it does have its uses, particularly as an introduction to the topic. So when we had that gas bulb here and the big gas bulb over here and open the valve, then the gas moved in to increase disorder. That was the driving force for the reaction. Now, if we look back to the mathematical progression of this concept of entropy from Clausius and from those that worked after him, we actually need to look at entropy in terms of statistics, in terms of probabilities. So what we discover is that the number of possible arrangements of molecules due to the fact that we open that valve has increased. In other words, these molecules can arrange themselves in more different states. We call them microstates. And I've got a slide coming up where hopefully I really simplify it so we get a better idea of what we're discussing here in terms of higher probabilities existing. But when you have the same number of molecules and more space, you have more probabilities, different ways that they can arrange themselves. That's the actual explanation for entropy. So here we have, in this slide, we have two bulbs and they're connected, and we have 4 molecules, just 4. Okay. So what's the probability? How many microstates can we have where all of these molecules are only in the left-hand bulb? There's only one possibility. Right? That's one possible microstate. If we move one of them over to the right, how many possibilities can we have there? Well, you can move the A over, or you can leave it behind and move the B over here, or you can move the C, or you can move the D. So we have 4 possible microstates with that one, where 3 are on the left and 1's on the right. If we put 2 on the right and 2 on the left, then we have 6 possible states. If we put 3 on the right and leave 1 behind, we again only have 4 states. And if we have all of them on the right, we only have 1 state. So which one is the most likely? The middle one, right? There are more possible microstates there with the middle. And that one says that we've got the same number of molecules on both sides. Okay. All right. Now, if we look at this in terms of, there are 2 ways to approach this microstate situation. One is positional. And that's the one we focused on so far, positional entropy. Positional entropy only looks at how many possible places can these molecules go, can they occupy? And that previous slide showed that we had for just 4 in 2 bulbs, the middle one with 6 possible states was the maximum positional entropy. And when we look at solids, liquids versus gases, we find that the solid is more ordered and it has fewer possible microstates because all the molecules are locked in place. So they can have some vibrational, but their positional entropies are fixed in that solid. Whereas a liquid may occupy a similar volume, but the molecules can slide past one another. So in that same volume, you can have multiple different microstates, depending on where each of the molecules is located. And we're still talking about positional entropy. Now, when you expand that liquid into a gas, now you have many more positional positions because if you take the same amount of liquid and make a gas out of it, the rule of thumb is it will expand about 1,000 times in volume. That varies all over the place, but roughly, rule of thumb, it's about 1,000 times increase in volume. So you've got the same number of molecules in 1,000 times the space. So you've got more positions that they can occupy in that added space. So for that, we're saying that the entropy of a solid is less than the entropy of a liquid, which is much less than the entropy of a gas in terms of positions of the molecules. Positions, possible locations, or arrangements, that's a better word, possible arrangements that they can occupy. So this discussion is not covered in your textbook. That was positional entropy. Now, there's another way of looking at it, and this is energy entropy. Energy entropy also considers the total randomness of the system and the surroundings during a process. And it has to do with, well, if a molecule has more energy, it can be in the second place quicker because it's moving faster. So if we increase the energy of a system, we are increasing its energy entropy. Now, we may also at the same time affect its positional entropy. If we heat it up, right, we can heat up the liquid. And as we heat up the liquid, we add to its energy entropy. When it turns to a gas, now we've got some positional entropy added on top of that. So they very often occur at the same time. In terms of the type of reaction, whether it's exothermic or endothermic, the exothermic reaction implies an increase in energy randomness for the surroundings. Right? So when we have an exothermic, right, system surroundings, and we're delivering heat to the surroundings, we are affecting the surroundings and increasing the entropy of the surroundings. So what's happening to the system? The energy entropy of the system is decreasing. If we transfer energy out of the system, then its energy entropy is decreasing. So there's sort of a balance here between system and surroundings in terms of energy. And endothermic goes the other way. Right? So if we transfer heat into the system, we are increasing the system energy entropy and decreasing the surrounding energy entropy. Okay, so let's look at these examples and see if we can qualitatively assess their changes in entropy. So what would be the sign for the first one? Evaporation of alcohol. Right, we're going from liquid to gas. So what would be the sign on the entropy? Increasing entropy is positive. Okay, so change in entropy here would be positive, correct? Okay. And here it's useful to use that disorder concept. It works. How about the freezing of water? So if we have water going from liquid to solid, what's happening to its entropy? It's decreasing. Okay. How about compressing the ideal gas at constant temperature? So we've got a change in volume. Change in volume is negative. Yeah, we're decreasing the volume of the gas. Let's see. I'll talk about that in just a second. There we go. Positive, negative, and this one is also negative. We are decreasing the entropy of the gas because we are giving those molecules smaller space to occupy. They have fewer positional states that they can occupy. Heating an ideal gas at constant pressure. So we're going to increase the energy. We're going to, let's see. We're going to add energy to it, heat. That would change the energy entropy by increasing. Okay. How about dissolving sodium chloride in water? The sodium chloride solid goes to sodium chloride aqueous. How about that? Well, if we're talking about the sodium chloride, we're definitely going from a solid to more dispersed ions. Right? So the entropy should increase for that. There we go. Okay, about that topic at the top, that note. Change in entropy cannot be measured directly. That is true. It has to be calculated using a formula. And this was developed by Boltzmann. So there were a lot of people working on this. Clausius introduced the topic, but then it took a lot of other people to work out the details. So this entropy S equals K times log W. Or it can be inferred from other equations. And the W there, I believe, is a work function. And K is a constant. Sometimes we call it a fudge factor. Just to make the units of entropy jive with the units of work. You don't have to know that. It's just an interesting fact. So, what was the first law of thermodynamics? Let's get these in order. First law of thermodynamics. Change in energy for the universe is zero. Right? The total energy in the universe is constant. Second law of thermodynamics has to do with entropy. First law, second law. So we introduced the concept of entropy for the first law. And all it says is that in any spontaneous process, there's always an increase in entropy of the universe. So we would write that like I did before. So for the whole universe, entropy is always greater than zero. But if we restrict or isolate our part of the universe, then entropy can go the other direction. That's a caveat. We isolate the system and the surroundings. All right. Now, we can also assess this change in entropy for, instead of saying universe, I'm going to say total. So the total entropy of our system surroundings is equal to the entropy change of the system plus the entropy change for the surroundings. That makes more sense to me, because there's no way we can get a handle on the whole universe. I mean, that may be true, but this is where we're going to focus our attention. What's the total? And it's a system and surroundings together. We can assess the change in entropy for our system and surroundings together if we have an idea of the surroundings and the system, what their entropies are. And like I showed you earlier, when we transfer heat out of our system, we're increasing the surroundings entropy and decreasing the systems. So there's a balance there. Where's my? So this is the one I prefer, where we have delta S total. It's more realistic anyway. So to predict spontaneity, if the delta S is greater than 0, the delta S total is greater than 0, then we're predicting that the entropy is increasing and the process is spontaneous. If this is negative, then the process is non-spontaneous in its current direction, but in the reverse direction, it will be spontaneous. And then if this is 0, that means the process has no tendency to occur and we're at equilibrium. So under an equilibrium situation, then these two would be equal and opposite. Okay. So for an example, if we have something that's in the liquid state and we change it to the solid state, which direction involves an increase in energy randomness or positional randomness? Okay, so let's look at it. Let's look at it from both perspectives. We've got an something in the liquid state, and it goes to the solid state. How about positional randomness? I know it's energy randomness first. Okay, we'll take energy randomness first. So we know that when we go from left to right, when we go from liquid to solid, we're exothermic, we're giving off energy. So the system would decrease in energy randomness. Positional randomness, though, is also a decrease. You're going from liquid to solid. Right, so you have fewer microstates, and that means that your positional randomness is also decreasing. So what's the balance between the two? Well, they're both decreasing, right? Going from liquid to solid, they're both decreasing. So if we consider both of them together, as temperature increases, positional randomness dominates. Okay. What we're trying to do is get a balanced understanding of positional versus energy randomness. So as the temperature, what does it do? Increase or decrease? which takes precedence when we go through this change. As temperature increases, the positional randomness dominates. So the energy, if we increase energy this way, then the positional dominates. It's more, it's the condition that drives the process. That's a better way of putting it. As the temperature increases, the positions that are occupied, the possible microstates, the positions occupied, dominates process. So at high temperature, the positional randomness would dominate because the energy is so high. And the energy change becomes less important. Here's the way I look at it. If I've got, say I'm a millionaire. So I've got $1 million. So I have $1 million. And somebody's going to give me $1. What effect would that have on my total wealth? Almost nothing. So at high temperature, the any addition of energy, so if we consider this as high temperature, then if we add temperature to that effect, it has little effect on the overall. So we defer to the positional randomness in this case. The converse, of course, is as the temperature decreases, say if my net worth is only $10,000 and somebody wants to give me $1. Well, it has more impact on my total wealth than it would if I had $1 million. So as the temperature decreases, say at low temperature, let's just say I'm really in tough shape. I've only got $100 to my name. Students can relate to that. Then if somebody wants to give me $1, that has a 10% increase. All right, so when we get low temperature, then energy randomness dominates over positional, because any addition of energy has a higher percentage impact on the energy randomness at low temperature. Okay, I hope that made sense. So at what temperature is there a balance between energy and positional randomness? Well, what we observe is that at an equilibrium point, so where do we have equilibrium points when we're talking about phase changes in particular? So we have a phase change in this situation here. Where do we have a balance between solid and liquid? The balance is when they're both present at the same time at the melting point. So temperature equals at the, well, you could say freezing point or melting point, either one. Melting point. At the melting point, you've got both. You've got both solid and liquid. And under those situations, then we have a balance between energy and positional entropy. So let's see if we can make sense when we apply them to other situations. So if we have a situation where, let's see, let me erase this and make room. If we have a situation which is exothermic, right, so we have our system and some change is occurring where it's losing energy, it's exothermic. But it becomes more positionally random. So if it's exothermic and becoming positionally random, then the volume would have to be increasing. We'd have to lose energy and increase volume. So if we're losing energy, then the temperature is decreasing. The change in temperature is negative. So as we're decreasing the temperature, which becomes more important, positional or energy? Energy becomes more important. And oh, I was answering the wrong question. Is this spontaneous or non-spontaneous? Well, if we're losing energy and we're actually the positional entropy is favorable because we're expanding. The exothermic, if it's exothermic, then we're losing energy. I don't get that one. Why would both driving forces be? The energy entropy is actually decreasing for our system. So let me think about that one. Let's look at the next one to see if it helps make sense of the others. Exothermic and becomes less positionally random. If it's less positionally random, then it's shrinking in some form. So in that case, you would need to know both of them. Which one is bigger? Right, this change or that change? What effect would it have on the overall? If it's endothermic and becomes more positionally random, and we can't tell that one either. But if it's endothermic and it's less positionally random, then that's not spontaneous. We're also going to say that A and D are not affected by temperature. Right, so A and D are situations where the energy entropy is less important. So that's why A is spontaneous with this more positionally random. When it's exothermic or it's endothermic, it doesn't matter. All right. Let's leave that topic behind for now. And look at the sign of delta S for surroundings. It depends on the direction of heat flow. If the heat is flowing into the surroundings, we should see an increase in entropy. Right? If heat leaves the system, then the randomness in the surroundings is increasing. And the system is exothermic. Delta H is negative. If the heat enters the system, then the randomness in the surroundings is decreasing. And the system is experiencing an endothermic change. If the magnitude of the change in entropy in the surroundings, well, the magnitude does depend upon temperature. So the change in entropy has a greater effect on the surroundings when it starts at a lower entropy than if it starts at a greater entropy. You add $1 to $100 has a greater effect than if you add $1 to $1,000,000. So for the surroundings, if the temperature is relatively low, then the change in entropy will have a much greater effect. So what we're saying is the change in entropy for the surroundings is directly proportional to the heat transferred and inversely proportional to the temperature. All right, the reason we're saying this is the next slide. We're saying that the change in entropy for the surroundings is directly proportional to the heat transfer or a change in temperature. So that would be up here in the numerator. These would be directly proportional. As this one goes up, that one goes up. And inversely proportional to the, inversely proportional to the temperature. I'm sorry. Inversely proportional to temperature, directly proportional to the heat. So the entropy change in the surroundings is directly proportional to the heat transfer and inversely proportional to its temperature. So that's really not temperature change. That's absolute T. Oops. There we go. So this is in terms of joules, and this is in terms of K. And if we write that, I thought we were going to get that written. An exothermic process, excuse me, let me go back. Yeah, okay. So we're going to see a change in entropy for the surroundings dependent upon if the heat transfer is high and the temperature is low, then this value is going to be large. This is easier to understand, I think, than all that wordy stuff to begin with. If the heat transfer is high, it's an exothermic process for the system. Right? So when we say exothermic for the system, that means we're adding heat to the surroundings. And if the temperature is low, then this value is going to be higher. But if the temperature is very high, and then we have a quantity of heat being added to it, it has less effect on the delta. Okay? Does that make sense? We're starting at a temperature that's high, then the heat transfer has less effect on the delta S of the surroundings. If we start off with a temperature that's low, then this value has a greater effect on the entropy of the surroundings. Okay. So notice that we're using enthalpy here. And we also have to change the sign, because if the enthalpy is exothermic, then it's going to be a negative. But that would decrease this value. So we have to fudge it here with a negative. And then the negatives, because now this puts this in, is referencing the surroundings. Without the negative, we're referencing the system. Okay, now we're going to digress just a little bit in order to, now what I've done here is equate Q in delta H, but that's not entirely true. They're two different concepts. Heat transfer versus change in enthalpy. They mean two different things. Enthalpy is a thermodynamic potential. That is, it's considered as something that's not realized, but it's available. Much like internal energy. And these are state functions. In other words, it doesn't matter how you get there. And we define it in these terms. Delta H is equaling, we did this a little earlier, plus the change in pressure times volume. All right. If we look at the equivalence, so what is delta E equal to? Remember, delta E is equal to Q plus W. So heat transfer and work relative to the system is that. If we insert these values in here, now we get delta H equals Q plus W plus delta PV. Okay. Come on, there. If the process takes place at constant pressure, then this P comes outside. And now we're just looking at a change in volume. Okay. Q plus W. All right. There we go. Now, we said earlier that W equals a negative P times the delta P. And I think, didn't we do this in calorimetry? Well, you weren't there for that class. But I think we did do this explanation when we talked about calorimetry, trying to differentiate between delta H and Q. So this is kind of a rehash. But we did determine that work is equal to negative pressure times change in volume. And we had to put that negative in there because of the example we were using, the model that we were using would have given us a positive value when W needs to be negative. But if we substitute that one in here, negative P delta V, and then Q P delta V delta H, then these two cancel one another. And that says that enthalpy and Q are equal only if pressure is constant. If pressure changes, then they're not equal. Well, that's why chemists conduct experiments very often in terms of constant pressure. If you can maintain constant pressure and measure the heat transfer, then that allows you to measure enthalpy as well. All right. So now let's get back to spontaneity. Can we use our expression for total entropy is equal to the entropy change of the system plus the entropy change of the surroundings. Okay. So actually, let me put them in the same order they have them. Only I'm going to identify ours as total. The slide has it as universe, but we're actually talking about total. So if this is a positive value, and this is a positive value, then when you add them together, you always get a positive value here. So that says spontaneous. If they're both negative, as written, then this is a negative value, and it's non-spontaneous. No reaction will occur in the direction as written, but it will be spontaneous in the opposite direction. Right? If this is positive and that's negative, then it depends on the size of this one. If this one is larger than surroundings, then it will be spontaneous. So system must be greater than, oops, excuse me, the delta S for the surroundings. This one has to be bigger than that one in order for this one to be positive. That's the only time that it would be a spontaneous process. And if this one is negative and this one's positive, then the delta S for the surroundings would have to be greater than the delta S for the system in order for it to be positive. Okay. So this one is conditional spontaneity, conditional spontaneity. This is always non-spontaneous. This one is always spontaneous. All right. So now we're going to talk about the work of this rather intelligent chemist, Josiah Willard Gibbs. Gibbs was interested in, okay, we know things about the reaction, right? We can measure heat transfers. We can measure total energy, right? We can measure this one. We can say internal energy is equal to Q plus W. Right? We can measure those things. We can equate that here plus P times delta V. We can do that. What Gibbs wanted to know was, as a practical matter, how much of this work, how much of this energy is available to do work, right? And that's a maximum theoretical amount. How much is the maximum amount of work that can be performed by a given process, taking into account all these factors, including entropy. So this is the equation that Gibbs proposed. And this is known as Gibbs free energy change. We need to know the enthalpy, and then we need to know both the temperature at which it occurs and the change in entropy. So this is Gibbs' equation. There are other equations that speak to the concept of useful energy for doing work, but this is the most commonly used. So we're gonna sit here and focus on this one. All right. If we divide the entire equation through by temperature, right? That's what we've done here, and that gives us oh, and we change the sign, right? So we throw a negative through the whole thing. If we do that, then this becomes negative delta G over T, and this becomes negative delta H over T, and this just becomes T's cancel, right? And this becomes a positive entropy. That's where that next equation came from. We did those two things, negative divided by T. Now, if we know that delta S for surroundings, and this is delta S for the system. So if we know that delta S for the surroundings equals a negative delta H over T. There we go. Then we can substitute that here into this position. And remember, anytime, that's what that parentheses means right here. If there is no subscript, assume that the delta S is referring to the system. Okay. So if we now substitute this in here, then this is delta S for the surroundings plus delta S for the system. That's what we were saying here, system. System. Okay. And that's minus delta G over T. Okay. So far, so good. But this expression right here is equal to the total entropy for the system. So the total entropy for the system, let's erase this stuff right here. So the outcome of this mathematical gymnastics is that the delta S total for the system, the delta S total for the process is equal to a negative delta G over T. And remember, if this is positive, then we have a spontaneous process. Right? If the delta S total is positive, it's spontaneous. So now we have a handle on this Gibbs free energy and temperature term. If this term over here is positive, then this is positive, and the process is spontaneous. Okay. That's the takeaway from all this working here, is this equation right here. You want to keep this one unmodified, delta G equals delta H minus T delta S for the system. And delta S total equals negative delta G over T. That's the takeaway. In this case, the way to interpret this is that if the temperature is stable, if it's constant, and also by definition, if the pressure is constant, then the delta S is spontaneous and it's positive. This is positive only when delta G is negative. All right. So if delta G is negative, then that means this term is positive and delta S is positive. This process is spontaneous. So the takeaway here is, if you have a delta G that's negative for any reaction, then the delta S is going to be positive and spontaneous. So let's take a look at these examples. Let me flip to my hard copy and see where we're at. It's 10:15. What do we have till? We have to 12:20. Okay. Yeah. Okay. We got a little ways to go. So a liquid is vaporized at its boiling point, that is constant pressure. So we're going from a liquid to a gas at the boiling point. That's the system we're interested in. That liquid is being vaporized at its boiling point. So you have both liquid and gas present at the same time, under constant pressure. Okay, how about the signs? Let's see if we can predict the signs for these. So if it's vaporizing, going from liquid to gas, what is required? Well, think of the system here. This is your gas. Excuse me. This is your liquid. And it's going to a gas. right? That's the system. It's the surroundings. What type of work is being done? Well, as it goes from a liquid to a gas, in order to maintain constant pressure, correct? The volume has to increase. So the volume here, right? The volume change would be positive. You'd have to increase the volume. And in order to do that, you're doing work on the surroundings. So the work that's being done here is negative. As you vaporize from liquid to gas, constant pressure, volume has to increase. Boyle's law. One goes up, the other goes down. One goes down, the other goes up. Or if pressure is constant, then the volume must increase. In order to accommodate these extra gas molecules, the volume must increase. So it's doing work on its surroundings. That's why W is negative. Right? How about Q? How's the heat being transferred? Q is going into the system in order to make this phase transformation occur. Right? Heat is required. We must provide heat from the surroundings in order to phase change from liquid to gas. How about delta H? Well, pressure is constant, right? If pressure is constant, then delta H is the same as Q. All right. How about delta S of the system? Well, we're adding energy to the system, so energy entropy is increasing, and we're making gas from a liquid. Positional energy is increasing because the volume has to expand in order to maintain pressure. So delta S for the system should be positive. All right. How about the delta S for the surroundings? Surroundings. What's happening to the surroundings? The surroundings are losing energy. Their energy entropy is decreasing. Plus, we are doing work on them and expanding our volume of the system, so the volume of the surroundings must be decreasing. That should also decrease the entropy of the surroundings. How about delta G? All right. What do we say about delta G? System. The delta S for the system, delta S total is equal to negative delta G over T. What's delta S total? Well, it depends on these two values right here. Which one is bigger? Of course, I left out this part. This is a phase change. We are essentially at equilibrium. And at equilibrium, delta G is equal to 0. All right. Free energy change for a phase change is always 0. Okay. Let's see. Delta H, we'll put this up here and see if it makes sense. Delta S. If this is system, delta S for surroundings, remember, is negative delta H over T. At equilibrium, they must balance one another. So all we have to do is change the sign. So this one is going to be delta H over T, which cancels the T, and delta H equals delta H. So what we've got is an equilibrium situation where the delta S's are balanced. And we can also say this, Gibbs free energy equation, right? Delta G equals delta H minus T delta S. Then if this is zero, then this arrangement here is zero. So this term has to be equal to that term. This one is positive. That one can be positive, and then we subtract it, makes zero. All right. Let's try another one. Let's see, one more of these, and then we get to listen to Professor Dave. The value of delta H of vaporization. What's the heat of vaporization of a substance? X. Well, we're given this information. The heat of vaporization is equal to 45.7 kilojoules per mole. Okay. And its normal boiling point is 72.5 degrees. So the temperature boiling point equals 72.5 degrees C. And it says the normal boiling point. Normal means 1 atmosphere pressure. So pressure equals 1 atmosphere. Those are all given facts. Calculate the delta S for the system, for the surroundings, and delta G for the vaporization of 1 mole of the substance at 72.5 degrees and 1 atmosphere. All right. At the boiling point, we know that delta G is equal to 0. And the delta S for the surroundings is equal to this term, delta H over T, right? So if we insert the delta H here, negative 45.7 kilojoule per mole, divided by the temperature, which is this one plus 273. Yeah, we're just using 273. Okay. 345 K. All right. Then we divide those out and we get a negative. All right, we changed this to joules. That's another fact that I didn't mention. When you see delta S reported in the literature, it will be in terms of joules per mole. Whereas most delta H's are kilojoules per mole. So you got to watch out for those values. So here we change this to joules, just multiply it by 1,000. Then when we divide it out, we get a negative 132 joules per K mole, right? Because this mole is in the denominator, it's over here. Okay, so that's the delta S for the surroundings. At equilibrium, the delta S total at equilibrium is equal to 0. And that's equal to delta S system plus delta S surroundings. So if this is 0 at equilibrium, and we say it's equilibrium here because we're at the boiling point, then if this is surroundings, then this has to be system. So the system is going to be a positive. 132 joules per k-mole. Okay. There we go. So we answered all three questions. And the key to this whole thing was it's at the boiling point. We're at equilibrium, thermodynamically speaking. Oh, here's Dave. Let's give Professor Dave a few minutes.
Professor Dave here. Let's learn the laws of thermodynamics.
He knows a lot about the science stuff. Professor Dave explains.
The laws of thermodynamics help us understand why energy flows in certain directions and in certain ways. A lot of the concepts described by thermodynamics seem like common sense, but there is a layer of math beneath the intuitive level that makes them very powerful at describing systems and making predictions. We won't get into the math, but we should be able to describe these laws conceptually. The first law, described in the most basic way, highlights conservation of energy. Energy is not created or destroyed, it only changes forms, from potential energy to kinetic energy to heat energy, etc. While we have found this to be untrue on the quantum level, for chemists it does just fine. However, there seems to be a preferred direction in which energy flows from one form to another. In order to understand why, we look at the second law. The second law introduces a new concept, entropy. Entropy is quite difficult to understand, but we can most easily describe entropy as disorder. And the second law states that the sum of the entropies of a system and its surroundings must always increase. In other words, the entropy or the disorder of the universe is always increasing. Within a system, there is also a tendency to go towards higher entropy. The classic analogy is that your bedroom will over time become messy, but it won't suddenly become neat. Another way to look at this is to say that entropy is a measure of how dispersed the energy of the system is amongst the ways that system can contain energy. Yet another way is to analogize entropic states to computer code. Let's take, for example, an ionic solid compared to the same substance as a liquid. Clearly, the solid state is more ordered and the liquid state is more disordered or higher in entropy. To describe the solid state using computer code, you would need to include terms that describe the geometry of the lattice, the intermolecular distances, the precise configuration of every molecule, and many other things. But to describe the liquid state, you would need to simply describe the volume of liquid and the shape of the vessel, because the motion and configuration of the molecules are random. That's far less information that needs encoding, which is a way of rationalizing why increasing the entropy of a system is thermodynamically favorable. We can look at all kinds of processes to highlight entropic influence. Heat will flow from a hot coffee cup into the table or your hand because the heat energy will be more disordered if more dispersed. This is why heat spontaneously flows from hot to cold and not the other way around, entropy. The third law states that a perfectly crystalline solid at absolute zero has an entropy of zero, as this is the most ordered state the substance can be in. Entropy is measured in joules per Kelvin. Note that entropy is not a measure of energy itself, but of how energy is distributed within a system. It is enthalpy, the thermodynamic quantity we learned about before, that is more accurately describing the energy of a system. As we will see, enthalpy and entropy intricately relate to tell us something about the Gibbs free energy of a system. G, or Gibbs free energy, tells us whether a process will be spontaneous or not, meaning if it will simply happen on its own. Change in Gibbs free energy is given by this equation, which includes change in enthalpy, change in entropy, and temperature. If delta G is negative, the process is spontaneous. If positive, it is non-spontaneous. So we can use this equation to see how a spontaneous process can be either enthalpically or entropically favorable, or both, but not neither. For example, if delta H is negative, which means exothermic and energetically favorable, And delta S is positive, which means an increase in entropy, which is also favorable. A negative minus a positive will always be negative, or spontaneous. If the opposite is true, and both are unfavorable, we have a positive minus a negative, which will always be positive, or non-spontaneous. If only one of the two is favorable, we have to do some math. If delta H is positive or endothermic, that energetic unfavorability could be outweighed by the other term if the process is entropically favorable. And since T is here, this factor will increase with a larger T, so entropically favorable processes are more likely to be spontaneous at higher temperatures. Conversely, if it is energetically favorable but entropically unfavorable, the entropic unfavorability will be minimized at lower temperatures. This is a very important equation to understand because it describes all of the spontaneous processes in the universe. There are those who incorrectly use entropy and the second law of thermodynamics to imply that order can't happen spontaneously. But we just showed that entropically unfavorable processes can be spontaneous at lower temperatures if they are energetically favorable. An example of this is soap. You need soap to wash non-polar dirt and grime off your hands because they are immiscible with polar water molecules. But soap molecules have polar heads and long non-polar tails, which allows them to spontaneously form structures called micelles. These are spheres where the soap molecules orient themselves with the polar heads facing out in order to maximize ion-dipole interactions with water molecules that bring the system to a lower energy. And the nonpolar tails will all face in, trapping the dirt by making a network of van der Waals interactions. The dirt trapped in the micelles washes away because the micelle as a whole is water-soluble due to the polar heads facing out. That's how soap works. And that's also how highly ordered structures can form spontaneously if by enthalpically favorable or energy-storing processes. In this way, systems can defy entropy on the small scale, but the second law does hold true in that the entropy of the universe is always increasing. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay, so be sure I'm on the right slide. Yeah. I hope that was a better explanation than mine. Definitely more concise. So, if we look at any process, chemical reaction, and we consider both the entropy of the system and the enthalpy of the system, any changes in the entropy and the enthalpy, then we can use Gibbs free energy equation to determine whether the reaction is spontaneous and under what conditions it would be spontaneous. So we have our equation, delta H minus T delta S. Okay. So under the first condition, we have delta S is positive and delta H is negative. So under what conditions would delta G be negative, spontaneous. Well, the variable here is temperature. If temperature, anything from 0K up is going to be, of course, a value for temperature, and this is positive. And then this whole term is multiplied by a negative, which means negative times negative equals negative. So any temperature will give you a spontaneous reaction. If the delta H is negative, exothermic, and the delta S is positive, more disordered. If delta S is positive, okay, is our next situation, and delta H is positive, under what conditions will you get a negative here? Well, under these conditions, you need to find a set of conditions where the change in enthalpy is less important. You know, we talked about those a few slides ago. That happens when high temperature is in effect, where positional entropy is more important than temperature, than energy entropy. So when delta H is, when it's an endothermic process, then what you need is a very high temperature. That's the reasoning part. Mathematically speaking, in order to make this whole expression negative, this needs to be very high so it can offset this positive. Okay. If this is very high, that means the overall negative exceeds the amount of this one. All right, so under those conditions, you would have a spontaneous reaction. If it's endothermic, then you need high temperature. Under what conditions would be the other direction? A negative here for entropy, and a negative here for enthalpy. Under these conditions, where you have both negatives, now you need to minimize the effect of entropy. So we need a low temperature here, right, which keeps this negative, but doesn't offset it by multiplying this value times a negative, which would make a positive. So this whole term would be positive. So we need to minimize. That means at low temperature, if you have an exothermic reaction and the entropy is negative, then you need a low temperature to give you a spontaneous process. So what are the other options? See, negative, negative, positive, positive. We need a positive here and a negative here. Okay, under what conditions would this be spontaneous? Never, right? It doesn't matter what this value is. This one is always going to be positive. Right, times that negative would always be positive. This is always positive. That would never be negative. So if you got an endothermic process where the entropy is negative, entropy of the system is negative, it will never be spontaneous in the forward direction. Now in the reverse direction, yes, it would be this one. If you reverse the reaction, then it comes to this place. And now you get positive, negative, and it's always spontaneous. So a never spontaneous would be always spontaneous in the reverse direction. All right. Okay. And we got another what if here. At this point, I'm going to insert this discussion about one of the points that I was trying to make during the lecture today on the 10th of April. So let me share the PowerPoint slides that I want to replace. Let's see, share. Okay. And I'll find them here. There we go. All right, turn it into a slideshow. Okay. During the lecture today, I had a slide in the set that referred to a gas A and a gas B that combined to make a gas AB. And there was only one slide with it. And on the surface, it appeared to me that the slide was in error. But upon further inspection, I realized that the problem is not the slide itself, but in the terminology that's used and the meaning of the word bond energy. So let me try to explain. The reaction is going to combine A sub 2, which is two A atoms hooked together. So I'm going to write them this way. And the B, and it's going to produce two of those. Now, I've represented them as single bonds, but it doesn't matter. Whatever the bond is, the problem tells us that at constant temperature and pressure, we know that the bond energy here is greater than that of either this one or that one. Okay, what is meant by bond energy? When bond energy is reported in reference manuals or in your textbook for that matter, it's always reported as positive values. That's because the bond energy represents how much energy must be added to the bond in order to break it. Okay, so look at it this way. The bond energy, the energy level of this bond is down here. So if we have energy on this scale, then the energy here would be the bond energy of A to B. Whereas the bond energy and the amount of energy that's required to break the bond would be, let's represent it like that, would be this much energy. It would take that much energy to break the bond. But if the bond energy of A and B are over here somewhere, say, oh, I don't know, here maybe and here, just speculating, as long as the bond energy here is greater than it is here, then the bond energy required to break this bond is only that much, and the bond energy required to break this bond is, say, that much. So when we look at it that way, the bond energy for the product, as stated, the bond energy of AB is much greater than that of either reactant. This bond energy is greater than these because bond energy means the amount of energy it takes to break the bond. So if its energy level for this bond is down here, it takes more energy to break it than it does for these two. Okay, that's what that means. And then when we use the formula to determine the enthalpy of the reaction, then we want to sum up the energies of the reactants and subtract the energy of the products. That way, this value is a larger positive value because it takes that much input of energy, a positive value input of energy to break the bond. So this is a large number, whereas the summation over here is much smaller. In fact, it's probably even smaller than that, but we're not to scale. So understanding that this value is going to be much larger, takes more energy to break the bond, and it's a negative, then this one is a positive value and it's much smaller than that one, then the overall effect of the two is to have delta H be a negative value, and that makes it exothermic. Okay, all right. So now with that knowledge, we can answer the question, predict the signs of these terms: the change in enthalpy, the change in entropy for the surroundings, change in entropy for the system, and the total change in entropy. So I've got that on the second slide. Okay. So using this information, we know that using the previous understanding of energy, then we know that the energy of the reactants is greater than the energy of the products. It's a higher energy level, right? So when we form the product, this energy level drops down to from the reactants to the product, and that looks more familiar. For this energy, it would be reactants here, products there, and we go up like that and back down. So that tells us in an absolute fashion, the energy of the reactants and the products decreases for the product, but the bond energy increases because in order to break the bond, we have to go from here to there. Whereas here, we only have to go from there to there. So with that understanding, this reaction is exothermic, and the sign for delta H is negative. Okay, now that we know that, we can relate that to the enthalpy, the entropy change for surroundings, because we know that the delta S for the surroundings equals negative delta H over T, and a negative is positive, so delta S for the surroundings has to be a positive value. Now the next one is a little trickier. We really don't have a handle on the delta S for the system. We can't say that it's opposite to the surroundings because we don't even know what the total is. So there's a bit of assumption here that the system entropy doesn't change because the pressure and the temperature don't change. But we don't know that for sure. We're speculating that the change in the entropy for the system is near zero. So then if we add them together, that still makes the total entropy greater than zero. Okay, so that I hope explains better the one slide, which is now 2 slides in this presentation, and from here we'll continue with the in-class presentation. Professor Dave talked about the third law of thermodynamics. And this is not earth-shaking. It's just, and it's important to those who study this stuff. So the only time we know, I shouldn't say no, the only time that we can predict that the entropy of a system is zero, right? There is no disorder, there's no energy disorder, there's no positional disorder, is with a perfect crystal at 0 K. And that's almost like a postulate. We're saying, yeah, it has to be. Entropy has to be 0 at that place for other reasons. So entropy is always positive. Change in entropy, actually absolute entropy is always positive value. And everything has an entropy. Remember when we were doing calculations with calorimetry, and we were doing enthalpies. Some enthalpies would be considered 0. In other words, an element that is in its normal state at 1 atmosphere pressure and 0 degrees Celsius, or a standard temperature and pressure. It depends on whether it's gas or liquid solid. Under standard conditions, the enthalpy for that element would be considered 0. That's our reference point. But for entropies, everything has an entropy. Elements, when you're calculating entropies for a reaction, everything in the reaction has an entropy value. So you look it up in a reference manual, you'll find a value for entropy for everything. Whereas elements, the enthalpies, some of them will be 0. All right, so when we calculate the standard, oh, I forgot to turn this back on. I don't know if I should. It's going to flicker, but I will. So the standard entropy has this 0 up here. And we're going to do it for the reaction. So what does that standard mean? That means standard temperature and pressure. At 0, at 298 K and 1 atmosphere. 273 plus 25 is 298. So what we need is the total of the standard entropies for the products, right? The total for the products entropies, and this depends on how many moles of each one this is. This is the coefficient in the equation. And this is for the products minus the standard entropy for the reactants. Okay. That's how we would calculate the entropy for a reaction. If the complexity of the molecule increases, we generally say the standard entropy increases. We illustrate this, our example here is the difference between water and diatomic hydrogen. So we see that for water, even if it's just one molecule, you get various vibrational states. So the first one you see is a bond stretch. So these bonds can stretch together, or they can vibrate back and forth, or they can stretch opposite to one another, or the whole molecule can spin. So you've got all these different possibilities for entropy for single molecules versus the hydrogen. Where's the hydrogen? Well, we don't give a picture, but hydrogen can only spin or it can stretch. That's it. So it doesn't have as many possible entropy states as a more complex molecule does. Okay, so if we calculate the standard entropy for this particular reaction, where sodium reacts with water to make sodium hydroxide and hydrogen gas, and we're given the following information, we just take 2 times the sodium hydroxide, which would be 100, right? So we take 2 times 50 for the sodium hydroxide, and then we add to that, what's the other product? Hydrogen. Notice hydrogen does have a value here in entropy, 131 times 1. 131. And then we subtract the reactants. And the reactant would be 2 times sodium, which would be 51. And then 2 times water, which would be 7. 2 times water, 7. There we go. And the standard entropy for that reaction should be minus 11 joules per K. So notice that's a negative number. Well, this is for the reaction. This is just for the system. Right? We can't tell whether it's spontaneous just by the system. We need the surroundings too. And it's more useful actually to calculate Gibbs free energy from this. Will Gibbs free energy be negative? Let's see, are we going to do that? Well, this gives us the standard entropy. Gibbs free energy would be just substitute here Gibbs in that same formula, and you can calculate the change in Gibbs free energy using a different set of values, of course. Well, they're not going to let us do it. I don't have that slide. Let's see. We will have some problems later. Okay, so don't panic. Let's take this example. See if we can make sense of this example. If this feels a bit overwhelming, don't worry about it. I mean, it stumps. Some people have been working in this for years. So if we have a stable diatomic molecule spontaneously forms from its atoms. So we have a diatomic molecule. Let's just take hydrogen, for example. Spontaneously forms from its atoms, right? So we're going like that. Predict the signs of these. Delta H, delta S, and that would be for the system, and delta G. All right, let's start with delta G first, because the key word there is spontaneous. It says this is spontaneous, so delta G has to be negative, correct? Let's see, did I do it backwards? No, I didn't do it backwards. Did I explain? Yeah, I did explain. All right, this is spontaneous because it's negative. Delta S is negative because it goes from more disordered to less disordered. This is more ordered, right? We take 2 separate atoms and make a molecule out of it. All right, so delta S is decreasing. And delta H, because this is lower energy than these two when we form the bond, then delta H is also negative. All right. So we're going to consider a more practical example here. If we have this reaction, PCl3 is a gas, PCl3 as a gas, and it reacts with chlorine gas. We set up a reaction here with producing PCl5 gas. Okay, and we're given delta G0. Delta G0. Standard Gibbs free energy is minus 92.50 kilojoules. Okay, What will happen to the ratio of partial pressure of PCl5 to partial pressure of PCl3 if the temperature is raised? All right, we're making a big leap here. All of these are gases, so that's good. Okay, what do we have? Well, let's see if this is balanced. Yeah, this is balanced. So we've got 1 mole here, 1 mole there, makes 1 mole here. So if the temperature is raised, this is a negative, so it is spontaneous. So delta G is equal to negative delta H over T, correct? Let's see if that's part of the explanation. Now, is that all we're going to tell us? I have to work this out on my own. Okay. They're working this problem from the Gibbs free energy. If we're saying, all right, we have to assume that what we're saying is that this is spontaneous, that direction. And we know that it's the delta G is a negative here. I want to be sure I got my formula correct. No, that's not right. That's delta S. Delta S surroundings, excuse me. Okay. Oh, delta S total. Is negative delta G over T. So we know that this one is negative, and a negative times a negative is positive. So that tells us that it's definitely spontaneous. Well, that tells us it's spontaneous. But the delta S is total. This is system. Okay. Delta S for the system is negative. Yet the reaction is spontaneous. Okay. The reason they're saying delta S is for the system is negative is because you have 1 mole here. You have 2 moles going to 1 mole. It's less ordered. That's why we're saying that the delta S for the system, we're saying that delta S for the system is negative. And we're claiming that with this value, it's unfavorable. That doesn't mean it's not spontaneous. That just means it's not favored by this going from 2 to 1. The delta S for the system doesn't favor it. We haven't drawn a conclusion yet on, well, we know it's spontaneous because this one is negative. Right? So if this one says that it's unfavorable because of 2 moles to 1 mole, then there must be something else driving the reaction. That means delta H has to be negative. If this is negative, then this one should be positive, and that would make this one negative. Right? So now we know that it's exothermic, and that makes it favorable. So as the temperature is increased, the reaction proceeds to the left. And if this is exothermic, I remember our little trick that we did with Le Chatelier. If it's exothermic, that means delta H is on this side. So if we increase the temperature, we're going to drive it back to the left. And if we drive it back to the left, what does that say about the ratio of partial pressure of PCl5 to that of PCl3? So the partial pressure of PCl5 over partial pressure of PCl3. We're producing less of this and more of this. This would decrease. Okay. That's all I can say about it. All right. Now, if we know all these things, these formulas, they do relate to one another. Up to this point, we've discussed the standard free energy change. But all reactions don't occur at those standard conditions of temperature and pressure. So what we need to do is get a handle on what's the relationship between the actual delta G of the reaction under the current conditions and other things like partial pressure or Q. You have feedback. You gotta go? Yeah. All right, I'll finish. I don't think we're too far from the end. And then next time we meet, we'll do that lab and review. So the delta G, let me see if I've got anybody else here, if it's just me. Oh, yeah. Okay. That's good. Everybody's still with me. So the actual delta G for the reaction determines whether it is spontaneous under the given conditions. If this is negative under standard temperature and pressure conditions, then the reaction will be spontaneous under those conditions. But what if we change the conditions? If we change the conditions, then we're influencing the reaction with this part, the ideal gas constant, and then the partial pressure. And that's not just partial, that's the total pressure in the system. So if we have a system where gases are involved, only gases, actually, you can have solids and liquids in here because they're not part of the equilibrium, right? So if we're determining this based upon pressure of a gas, that's what we would use. If we have a system where we have, say, solutions or a mixture of solutions and gases, then we can use the Q for our equilibrium. Calculate the Q, use the standard Gibbs free energy for that reaction, and you can calculate the actual Gibbs free energy and determine if it's spontaneous, because this influence on that value could throw a negative to a positive. And in this case, R is the constant with the energy term in it, not the liter atmospheres. Remember, liter atmospheres would be this one. But the one we want to use here is 8 point, I can do better than that. 8.3145, I believe it is. Joules per K mole. That's the one we would use for this equation. So we've got a little model here that we want to try to use to visualize the concept of delta G for a chemical reaction. The system, the one that we're discussing, the one where the chemical reaction is occurring, can achieve its lowest free energy state by going to equilibrium, not necessarily to completion. Right? So we could have reactants and products. We don't have to have reactants going all the way to products and no reactants left. For a phase change, we're looking at the left-hand side. Right? A phase change will take you eventually, you're undergoing phase change here, but eventually you end up with a single phase down here. Whereas for a chemical reaction, you can start off with reactants and you're producing some products and producing some products. And rather than going all the way to products, we have some happy medium in here where you have both reactants and products present and you're in an equilibrium state. The equilibrium state, the equilibrium point for a chemical reaction occurs at the lowest value of free energy. And that lowest value is 0. So in that case, the lowest value energy change here would be 0, which would be equal to delta G0 plus natural log of R, R first, then natural log of K. The reason we're using K and not Q is because we're at equilibrium, right? We've reached our lowest energy state. Now we have some reactants, some products, and they're going backwards and forwards. And we're at a stable position. That's where we use K. If we're at an unstable situation, a non-equilibrium situation, we would use a Q because we're not at 0. But since we're at an equilibrium, then the actual delta G is 0. And this 0 is equal to that. So what does that tell us? That means delta G 0 under these conditions of equilibrium is equal to a negative R log K. Okay. That means that we can, if we know the K value, which we have calculated other ways, then we can calculate, left out T, excuse me, RT. If we know the K, then we can calculate the delta G for that reaction under standard conditions. There we go. So I think what this slide is trying to do is to get us to look at the difference between how much in a reaction where A is going to be. A is a reactant, B is a product, and we're in equilibrium situation. Or we're trying to reach equilibrium. Then as the fraction of A decreases and the fraction of B increases, then we reach a situation here where we're at the lowest possible free energy state for A. And if we go past equilibrium, now we're trying to increase the equilibrium state of A. And that is unfavorable. We have to put energy in. So the slide says that an A gas goes to a B gas. There we go. And then we can calculate the free energy of each one. So the free energy of A is equal to the actual free energy of A is equal to the free energy of standard free energy of A plus RT log partial pressure of A. Okay. That was our first formula that we saw on that previous slide. We can do the same thing for B. Partial pressure of B. So what's the total for these? Well, the total is the summation of the two, right? They're in there together, and each gas has its own free energy. But the total for the system is determined by the summation of the two. So as A decreases, the Gibbs free energy of B is increasing. So as A disappears, the Gibbs free energy of A decreases, right? Because it's not there anymore. And the pressure, partial pressure of A decreases, right? So the Gibbs free energy of A is decreasing as the reaction proceeds. As B appears, the Gibbs free energy for the B increases because now we have some partial pressure for the B. As long as the Gibbs free energy of B is less than A, then the reaction will proceed to the right, because we want them to both be equal. Right? The Gibbs free energies of each one needs to be equal. So when we reach equilibrium, then this total must be zero. Remember, we discussed that earlier. The Gibbs free energy for the reaction is zero at equilibrium. And the only place that can occur is when these two are equal to one another. All right. So what can we say about K? Let's keep this one right here. This will help us with this particular discussion. If delta G 0 is equal to 0, then K is equal to 1. Because if this is 0, then this is a value, and this is a value, right? We can't do anything about that. So how can we make this side equal to 0? The only way we can make this side equal to 0 is if K equals 1. Right? The log of, the log of 1 is always equal to 0. And if we say this, where this is the base, and this is 1, then the base to what power equals 1? Has to be 0. There's always 0. So the log of this value, this value has to be equal to 1. So K would be equal to 1. And the log of 1, B to what power equals 0. Is equal to 1. B to what power equals 1, right? B to what power equals 1. B to what power equals 1. It has to be 0. So this one, this term would be 0, and 0 times this is 0. So under those conditions, K has to be equal to 1 in order for delta G0 to be equal to 0. All right, so what if delta G0 is less than 0, or negative? If it's negative, then the log of K must be positive. And for that to be true, K has to be greater than 1. If delta G is positive, right, or greater than 0, then K must be less than 1 in order to make this entire term greater than 0. So those are the relationships between delta G0 and K. And remember, this is under equilibrium conditions. If that's a Q, then all bets are off. It has to be K in order for these relationships to hold. All right, so let's shift gears a little bit. I think we're nearing the end. This is close to the end, last topics. Yeah, we have 5 more slides. So let's go back to Gibbs' original, and those working in the same area as him. Their original concern was how much of this energy change is available for useful work. Well, the premise says that the maximum amount of work is equal to the Gibbs free energy. The change in Gibbs free energy is equal to the maximum work. It may, and usually isn't, all the work that you can get from the change in free energy, because there are other factors that rob you of those of that available energy. But this is the maximum amount of work, and that means that okay. This only occurs for reversible processes. Okay. Most processes are irreversible, in which case the maximum amount of work is never actually reached. So how do we simulate reversible processes? Well, the way to simulate a reversible process is to make the changes infinitesimally small. Changes in volume, changes in pressure, changes in temperature, changes in entropy, make them very small in the real world, right? This is not standard conditions. This is under whatever conditions. So you change the conditions so that this one is extremely small. Then you can get reversibility in theory. Okay. So since the equilibrium point for a reaction occurs at the lowest value of free energy available to the reaction system, that is delta G equals 0, that's the lowest value possible. Then we have the situation where, again, delta G0 is equal to negative RT log K. So we want to approach this in terms of what's the relationship here between these two? Temperature and K. What's the interdependence here? So if we say that delta G 0 is also equal to delta H minus T delta S, right? That's Gibbs equation. Then at equilibrium, we can say that this one equals that one, right? If A equals B and B equals C, then in this case, B equals C minus RT log K equals delta H minus T delta S. Okay. Let's see. In this case, we want to divide the equation through by minus RT. So if we divide this one through, we're trying to get K on one side of the equation. So we can say, all right, what's it equal to? So if we divide the whole thing through by minus RT, now what do we get? Well, these terms drop out and we get log K is now equal to delta H over a negative delta H over RT, and then a positive delta S. Let's see. There. Then a positive delta S over R. Okay. Now we're getting there. In order to, what we want to do is rearrange this equation some way, which we've been doing, in order to get a straight line relationship. We want to know what's the relationship between K and temperature. So we're almost there. So if we have the log of K as our Y value, and we take negative delta H over R as our M value, and then 1 over T as our X value, right? See, it's in the denominator. So here's 1 over T, pull that out, and you're left with minus delta H over R, right? And then the B is just this one. So Y equals MX plus B. Y is log K. The slope is negative delta H over R. X values are the inverse of temperature. And the intercept, the Y-intercept, is delta S0 over R. So the next slide, I think, is going to plot these values. Here we go. All right, so if we plot these values, and on the x-axis we have 1 over T, and this is in this would be the units of measure would be K to the minus 1. Right? Temperature must be in K. And on this value we have log of K, and this is temperature K, this is equilibrium K, equilibrium constant. And when we plot them, we get a negative slope. So our values are going to be like this. Right? Negative slope. And the slope of this line, the slope of this line equals a negative delta H over R. So if we conduct an experiment where we determine K at different temperatures, then we plot the data, we can determine the enthalpy of the reaction by determining the slope and plugging it into this formula and solving for that one, because that's a constant. Okay, that gives us the delta H. The delta S0, let's see, this is 0 also. The delta S0 is the Y-intercept. So wherever it intercepts right here, that value is delta S0 over R. So we get the log value here, that value is equal to this. Delta S over R. So we just multiply by R and we have our standard enthalpy for that reaction. All right, this is just restating the obvious. The maximum of work that we can get from a spontaneous process only occurs when the pathway is reversible. Since it's not reversible, all real pathways waste some energy. All right, this is one way of saying it, of the laws of thermodynamics. So the first law says, right, delta E for the universe equals 0. There's no change in energy for the universe. What that means in this format is you can't win. Right? There's no way to win. Energy is the same no matter where you go. All over the universe, energy doesn't change. In other words, you can't win. And this law in itself just says you can break even because everything's equal to 0. You can't get more energy out of a system than you put into it. Second law, excuse me, wrong place. Second law says that the total entropy of the universe is always increasing. What that means is with the first one, you can't win, you can only break even. Second law says you can't even break even because any transfer of energy will result in some waste unless a temperature of absolute 0 can be achieved. Since we can never get to absolute 0, then we can never break even. We always lose something in the process. And the third law doesn't have a formula. It just says well, I guess it does. The entropy of a crystal, a perfect crystal at 0K is equal to 0. That just means that you can't get out of the game because you can never achieve absolute 0. We're stuck. We're stuck in the game. All right. Let's see, is that the last slide? Well, all of these laws taken together, anytime we use energy, we degrade its usefulness. In other words, we've got energy stored in the ground in fossil fuels, just not infinite, but pretty near infinite stores of energy in these fossil fuels. And anytime you use them, then the products that are produced by that reaction are less valuable. So we would go, say, for instance, we would go from, I don't know, let's keep it simple. Say we have methane and we add oxygen to it and we're going to make carbon dioxide and water. Right, so let's see, that would be 1 carbon, let's see, 2 here, so that means 2 here. There we go. So that's balanced. When we go from energy stored here to here, we extract energy, exothermic, right? And we use that energy. But in order to go back, we have to put energy in. In other words, this is a lower energy state than that. We have degraded its usefulness. We have increased the entropy of the system by this reaction. Now, we haven't made more moles of gas, right? 1 + 2 is 3 and 1 + 2 is 3. But we have decreased the or increased the energy entropy of the system. All right. So that's it. That's all for chapter 17. And if you need to focus on, there are 2 review documents. I split them because there were too many in one. If you need to focus your attention, focus on the second one, version 2.